video is going to be about gases. Now, temperature and pressure are directly proportional. This means that when volume is constant and temperature goes up, pressure will also go up. Same thing for temperature and volume. They're also directly proportional. So when pressure is constant, when temperature goes up, volume will also go up. Now, volume and pressure are indirectly proportional. This means that when temperature is constant and volume goes up, pressure goes down, which leads us to the combined gas law. P1 times V1 over T2 equals P2 times V2 over T1. Or you can say P1 times V1 times T2 equals P2 times V2 times T1. Now, pressure can be in any unit, so atmospheres, millimeters of mercury, or torr, and volume could be liters, milliliters, it doesn't matter. However, temperature has to be in kelvins, and finding kelvins is really easy. You just take degrees of Celsius and add 273 to it. Next is the ideal gas law, PV equals nRT. Pressure is in atmospheres, volume is in liters, temperature is in kelvins, N is the number of moles, R is a constant, 0.0821 liters atmospheres per Kelvin moles. A variation of this formula is PM equals DRT. I personally like to call it afternoon dirt, it's just an amusing way to remember it. Capital M is molecular mass and D is density. Now density equals mass over volume, so the units on that would be grams per liters, and the units of molecular mass is grams per mole. One of the problems is cyclopropane is composed of 85.7% carbon and 14.3% of hydrogen by mass. If 1.56 grams of cyclopropane has a volume of 1 liter at 0.984 atmospheres and 50 degrees Celsius, what is the molecular formula of cyclopropane? So, based off of the question, we know that there are 85.7 grams of carbon and 14.3 grams of hydrogen. From the periodic table, we find that there are 12.01 grams per mole of carbon and 1.01 grams per mole of hydrogen. We do a simple Stoich step here and find out that there are 7.136 moles of carbon and 14.158 moles of hydrogen. The reason we do this is to find the empirical formula. Now, when finding the empirical formula, you divide all the moles by the smallest mole. So you divide everything by 7.136, and you find out that there is 1 carbon and 2 hydrogens. So the empirical formula is CH2, and the molecular mass of that is 14.03 grams per mole. We want to know what the molecular mass of the molecular formula is, so we use afternoon dirt. It's a simple plug and chug. You just have to remember to convert Celsius into kelvins, and M should equal 42.0 grams per mole. You divide the molecular mass of the molecular formula by the molecular mass of the empirical formula to find the ratio between the two. And so when you do 42 divided by 14.03, you get 2.99 about. You can just round that up to 3 though. So it's a 3 to 1 ratio, meaning the molecular formula is 3 times as large as the empirical. So you can just times the empirical by 3 to find the molecular. And so now we know that the molecular formula of cyclopropane is C3H6. The next question is, judging from its molecular formula, would you expect cyclopropane to deviate more or less than argon from ideal gas behavior at moderately high pressures and room temperatures? Explain. Now, argon and cyclopropane are both nonpolar. They have similar molar masses, it's about 2 grams off, and both of them experience London dispersion forces. However, cyclopropane will have more intermolecular attractions than argon, so cyclopropane will deviate more under the specified conditions. You have to remember that in a gas, there are no attractive or repulsive forces between the molecules. So if the gas is ideal, that holds true. And since cyclopropane has more attraction, that's why it's less like an ideal gas. The next problem is a 6.53 gram sample of a mixture of magnesium carbonate and calcium carbonate is treated with excess hydrochloric acid. The resulting reaction produces 1.72 liters of carbon dioxide gas at 28 degrees Celsius and 743 torr pressure. Calculate the total number of moles of carbon dioxide that forms from these reactions. This is a simple PV equals nRT. The conversion between atmospheres and torr is just that 1 atmosphere equals 760 torr. You also have to convert 28 degrees Celsius into 301 kelvins. Just plug that all in after you do your conversions, and you should get 0.068 moles of carbon dioxide. The next problem is a little bit harder. Assume the reactions described above are complete. Calculate the percentage by mass of magnesium carbonate in the mixture. So there are two reactions going on. I wrote the equation for both. Magnesium carbonate plus hydrochloric acid yields magnesium chloride plus carbon dioxide plus water. And then there's also calcium carbonate plus hydrochloric acid yields calcium chloride plus carbon dioxide plus water. So we know that the mass of the total mixture equals the mass of every element in that mixture. So we can say that 6.53 grams equals grams of magnesium carbonate plus grams of calcium carbonate. However, since we do not know how much grams we have, we know that grams equals moles times molecular mass. So we can change the formula a bit and say 6.53 grams of moles of magnesium carbonate times the molecular mass of magnesium carbonate plus moles of calcium carbonate times the molecular mass of calcium carbonate. Now, after looking at the periodic table, we know that the molecular mass of magnesium carbonate is 84.32 grams per mole, and that the molecular mass of calcium carbonate is 100.09 grams per mole. We can just substitute that into our equation, and we notice that it is a 1-to-1 ratio of carbon dioxide to magnesium carbonate and calcium carbonate to carbon dioxide, which means we can say that the moles of carbon dioxide equals the moles of the mixture, which equals the moles of magnesium carbonate plus the moles of calcium carbonate, and that all equals 0.068 moles. Which, based off of this, we can say that moles of calcium carbonate equals 0.068 minus moles of magnesium carbonate. And we could put that into our equation from above, so we have everything in one variable, and we can solve for it. So I just made moles of magnesium carbonate X, and plugged it in, and I solved for X and found that X equaled 0.0175 moles of magnesium carbonate. However, the problem asks for the percentage of magnesium carbonate by mass, which means we need it in grams. So we have to do 0.0175 moles times the molecular mass of magnesium carbonate, which is 84.32 grams per mole, and we find out there are 1.4756 grams of magnesium carbonate. And when doing percents, it's just part over whole times 100. So you do 1.4756 over 6.53 times it by 100, and you should get roughly 22.6%. The last problem is gaseous iodine pentafluoride can be prepared by the reaction of solid iodine and gaseous fluorine. A 5-liter flask containing 10 grams of iodine is charged with 10 grams of fluoride, and the reaction proceeds until one of the reagents is completely consumed. After the reaction is complete, the temperature in the flask is 125 degrees Celsius. What's the mole fraction of iodine pentafluoride in the flask? So we have to find the limiting reagent, which you just do in an easy strength step, and you find out that iodine is the limiting reagent and that it produces 17.49 grams of iodine pentafluoride. So after we know that, we need to know how many moles of iodine pentafluoride are produced, since we're looking for the mole fraction. So you do 17.49 grams over 221.9 grams per mole, and you find out that there are 0.07882 moles of iodine pentafluoride. Since we know that iodine is the limiting reagent, that means there's not going to be any left over in the flask, so that does not need to be counted in our mole fraction. But we need to know, since this reaction is complete, how much fluoride was used up. So we start with our limiting reagent, we go to fluoride, and we find out in this first step that 7.486 grams of fluoride was used. So you have to be careful here and don't say that that's how much is left over, it's how much was used. So you minus it from the original 10 grams that you started with, and you find out that there's 2.514 grams of fluoride left. However, since, again, we are trying to find the mole fraction, you have to convert that back into moles, so you just do 2.514 grams divided by 38 grams per mole, and you know that there are now 0.0662 moles of fluoride. And now you can do your mole fraction. It's just part over whole, so 0.07882 all over 0.07882 plus 0.0662, and you find out that the mole fraction is 0.544. And that's it.